of CTU, and thank you for your interest in our talk. Today, we are so happy and honored to have Professor Shuyu from KAUST to give a talk. Professor Sun is a leading expert in computational mathematics, and currently he's a full professor at King Abdullah University of Science and Technology. Professor Sun is also leading the computational transport phenomena laboratory at KAUST, and he is also the founding president of International Society for Porous Media Saudi chapter. Before joining KAUST, Professor Sun served as an tenure track assistant professor of mathematical science at Clemson University in the United States. He obtained his PhD degree in computational and applied mathematics from the University of Texas at Austin. Professor Sun has ever held or is holding a number of adjunct faculty positions across the world, including adjunct faculty in Clemson University, University of Nevada at Las Vegas, Xiamen University, China University of Petroleum, and China University of Geoscience. Professor Sun is interested in the research of the modeling and simulation of porous media flow at Darcy scale, Paul scale, and molecular scale. And he had published over 400 articles or book chapters, including over 280 referred journal articles. So far, based on Google Scholar, his total citation number as of November 2021 is 6,383 with a H index of 38. 3 of his peer-reviewed papers have been recognized as highly cited in field in Web of Science. And recently, he also published a book with Elsevier entitled Reservoir Simulation, Machine Learning and Modeling. Today, Professor Sun will bring us a talk on phase-wise conservative and bound-preserving algorithm for multi-phase flow in geological porous media. Well, it's time for us to enjoy Professor Sun's excellent presentation. Let's welcome Professor Sun. Yeah, Professor Sun, it's all yours.
Thank you, Alina, for the introduction. And also thank you for inviting me to give a talk in this series. It's my great pleasure and honor to give a talk in this series organized by Department of Mathematics in the City University of Hong Kong. So today I want to talk about some of our recent works. By recent, I mean recent few years, recent 5 years. We put a great effort to develop a new framework for simulating multi-phase flow in geological porous media. Here's the outline. So first I'm going to talk about the background information, the motivation, the introduction, and some significance of the research. And in the second part of my talk, I'm going to review the current state of art simulation technology for multi-phase flow in porous media. Particularly, I'm going to emphasize the limitation for the current state of art technology, because if you read the textbook or papers, most likely and they're going to mention only the advantage, not too much on the limitation. So, so our research in this area, we actually focus on 2 different directions. One is the semi-implicit algorithm for the multi-phase flow simulation. Another one is fully implicit algorithm. We recently also have some work on deep learning technology applied for this reservoir simulation, but I don't think I have time to go through that. So finally, I'm going to conclude with some concluding remark. Okay, so first, some background information. So multi-phase flow in porous media, particularly in geological formation, is very important and has been widely used in many different area of engineering and industry and also environmental science. Particularly, I want to mention 2 major applications. One is from energy, another from environmental science. So conventionally, if you want to get the petroleum, oil or gas from the reservoir, initially, of course, if the pressure is high, the petroleum can come out to the surface by the pressure, high pressure in the reservoir. But later on, you have to inject certain fluid, like water, or sometimes we inject the gas to maintain the pressure in the reservoir. And then the efficiency of the displacement of oil and gas in the reservoir is highly depends on the operating condition and the well and the location of the well. So to optimize the profit of this process, the oil industry heavily depends on the information provided by numerical simulation for petroleum, water, and the other fluid flow in geological formation. I also want to mention that particularly in recent 10 or 12 months, there's a very hot keyword on carbon peak and carbon neutrality. So particularly, I think almost a year ago, China stated that China want to try his best to maintain the to get the carbon emission peak before 2030 and to achieve carbon neutrality before 2060. This is really ambitious goal, but we need a lot of technology to achieve this. Of course, many of technology listed in the slides, a lot of is related to the clean energy technology, particularly the thermal energy and the hydrogen energy. For thermal energy, of course, is also heavily depends on the multi-phase flow together with the heat transfer in porous media in the geological formation. And for hydrogen, of course, one of the bottleneck technology is how to storage of the hydrogen, because the storage and the transport is the main challenge here. And one of the storage technologies people propose is to store hydrogen in the subsurface. So again, we also have the same problem that we need to understand better and deeply how the gas can be safely or in long time stored in the subsurface. And CO2 sequestration has been also another technology to maintain the to reduce or balance the carbon emission. So instead of put a CO2 on some surface facility, so we actually want to store CO2 subsurface, particularly in some saline reservoir or depleted oil and gas reservoir and so on. And here we want, of course, the numerical simulation again can be a really helpful tool for us to understand how long the CO2 can remain there without escaping back to the surface. Particularly, I think initially when people study the four major trapping mechanisms for CO2 in the subsurface, they also heavily using numerical simulation too. I also want to mention about another application is this unconventional oil and gas, particularly shale, stored in this shale formation in the subsurface, is also a heavy, hot topic, particularly in China in recent 10 years. If we want to use nuclear energy, that's another way of clean energy. We also have to worry about how to store the nuclear waste coming from the nuclear energy industry. And typically, one of the safe method to store is to want to locate one of the very low permeable layer. Here in this illustration, we choose a clay layer to store this nuclear waste in a small repository in this layer. But unfortunately, in other neighboring layers, the permeability is high. So then to calculate or predict how long the nuclear waste can store in the subsurface safely, we have to solve a reactive diffusion convection equation, sometimes also coupled with the sorption reaction in multiple geological layers where the permeability can jump the magnitude of up to 6 order magnitude difference. So that's put a great challenge in numerical simulation as well. So in one method people doing this use a high order finite difference method for the spatial discretization to describe compositional multi-phase flow, which we also put certain efforts. In this case, particularly for the nuclear waste, because spatially there is a multi-scale in the space because they put in locally certain space, so the mesh adaptation might be useful. But however, time discretization scheme and also the decoupling scheme can be also crucial. So what I just mentioned so far is all talk about the Darcy scale. So Darcy scale is a scale like we could have a kilometer down to say centimeter or even millimeter scale, where Darcy equation can hold. But the Porous scale recently can be also interesting. So in my research lab, we also have like a number of students working on Porous scale simulation, particularly to develop new model for multi-phase, multi-component phase flow in a free space, where well, of course, the momentum equation is based on the commonly Navier-Stokes equation or certain modification of that. And if the pore is really tiny, particularly if the pore is like in nanometers size, the Navier-Stokes equation might not be accurate enough. So we also, in my group, we also have students working on the molecular dynamic simulation. So all the scale, of course, you will solve differential equation from even some in molecular scale is ODE system. In Porous scale and Darcy scale or PDE, partial differential equation. Certainly the time discretization will be crucial, which is a topic I'm gonna share in this talk. I want to also just list a number of the major model you might see in the papers from Darcy scale to the molecular scale. I want to say comment on that for Porous scale, if you want to do multi-component, multi-phase involving partially miscible fluid, and then even the model is not mature, so we put a lot of effort to develop the model. So, but of course, for single-phase flow, and then the model and the numerical algorithm is quite mature. In Darcy scale, more or less the model is mature, but numerical algorithm still have some room for improvements, which is a topic I'm going to talk about today. So, now I'm going to review some of commonly used algorithm people use for the multi-phase flow simulation at the Darcy scale. In oil industry, this is known as reservoir simulation. Of course, reservoir in oil industry is referred to the oil or gas reservoir. But of course, for environmental science or environmental protections, people also interested in the reservoir in the subsurface. For example, the water reservoir. We were interested in the contaminant in the water reservoir. So reservoir simulation too. So it is an important component for both major applications. As I mentioned, at the Darcy scale, typically we solve PD, partial differential equation. So spatial discretization and temporal discretization are needed. For spatial discretization, in my lab, we're interested in locally conservative algorithm because local mass conservation is important. We have mathematical reason for that. We have a paper for that, but well, I don't think I have time to go through that today. So the locally math conservative algorithm, we're interested in including the block center fine difference, which is commonly used in oil industry, and also mixed finite element method, and also as well as the discontinuous glycan. They are all locally conservative. For in terms of time discretization, we want so this actually is coupled with the decouple algorithm, particularly if you use fully explicit of semi-implicit algorithm, you need to decouple the equation. So in terms of time discretization, we can categorize it majorly in 3 major types. One is a fully explicit algorithm, where, for example, if you discretize the time derivative by finite difference, then all other variable you use a value from previous time. That's called fully explicit. And this, of course, is the simplest one, very easy to implement. But however, because of the severe CFL condition, the time step for stability is very tiny. So because of this, the computational efficiency is very low. So in practice, particularly in reservoir simulation, we don't use it. So in practice, we only use a fully implicit approach and the semi-implicit method. So fully implicit, if you use, for example, Euler Method, is also easy to understand. So you discretize the time derivative for example, the lowest order Euler, there's a finite difference formula, and then all the other variable you use the future value from the future time step. I mean, so you treat it implicitly. Of course, the challenge here is you end up with a large, a simultaneous system of a large number of unknowns, and also with a strong nonlinearity. So then you have to worry about how to solve this nonlinear equation. So basically, you shift the decoupling effort to this nonlinear solver, basically, if you use a fully implicit approach. So semi-implicit method sometimes can be also quite useful, because in terms of implementation is easier than fully implicit. For example, one challenge is you can solve certain sub-physics in certain sub-steps. And then in this way, you reduce the number of simultaneous unknown in your sub-step. And in certain time, you can also put a certain, those terms with a strong nonlinearity, you can treat that explicitly. If you do that, you actually linearize the system. So you don't need to, you have the option to design a linear semi-implicit algorithm as well. So this, so today we're gonna talk about both methods. Particularly, I'm gonna spend most of the time talking about semi-implicit, just because of the time. So I want because of this, I want to review one of the most popular algorithm people use in the industry for both the oil industry as well as the environmental science, and this is called a classical impasse algorithm. It's representing the implicit treatment for pressure and the explicit treatment for saturation. So the method has a lot of advantage. Due to time, I just want to mention that this algorithm, one of the success of why this algorithm works is because it's derived the pressure equation, where the dependence of the pressure equation is very weak on the saturation. So that's why if you do this decoupling, you do not commit too much decoupling error. And also, if you want to do iterative impasse, the conversion will be fast. And also, in this decoupling, the total velocity has a continuous normal component as physics require. So I want to just use a model equation. Of course, for porous media flow, you have a larger collection of different models. One of the simple model involved multi-phase flow will be this fully incompressible, fully immiscible two-phase flow in porous media. So we assume the fluid is incompressible, so density is constant. Therefore, mass conservation implies volume conservation as well. So the conservation law is written in this form. And that U here is Darcy velocity. So we have this equation for both wetting phase and non-wetting phase. Darcy velocity can be related to the gradient of pressure and the gravity term through this Darcy's law. This is also known as extended Darcy law for multi-phase flow. Then you have the summation constraint, and also you are giving the relative permeability as a function of saturation, as well as the capillary pressure as a function of saturation. Of course, both functions typically have a strong nonlinearity there, which causes a problem or challenging in numerical algorithm. So if you count how many unknown here, typically you depend how do you count, either 6 or 8 unknown you have, but we can easily see by local elimination. By local, I mean when you only spatially local, you can easily eliminate most of the unknown except for 2. All right. So this 2 unknown, you have to choose as your primary unknowns. Then you have to solve your global system to determine the primary unknown. So one choice, popular choice, is to choose say one saturation together with one pressure as our primary unknowns. The impasse algorithm we can derive by summing the 2 conservation law and to define certain collection number of intermediate variable for convenience. And then I'm assuming that most of the audience is familiar with it. So I just quickly to come up with a conclusion. So you get this pressure equations. So this equation, the unknown is the pressure for the non-wetting phase. Of course, after you get pressure, then you can quickly use a Darcy's law to recover wetting phase velocity as well as the total Darcy velocity. So to treat this one, we typically solve for Pn and we assume we know SW. So we put all the other terms through other terms to right hand side. So we define the right hand side function as a function SW, and you solve for Pn. Now for the other variable, typically we choose, for example, if you choose a wetting phase saturation as your primary unknown as well, then you just use a conservation law by substituting UW by using our UT, which will compute from the pressure equation. And unfortunately, due to the capillary pressure, UT have to come together with another high order term to get your UW here. So this is going to give us a saturation equation like this. And notice that the saturation equation involve second order spatial derivative for SW. All right, so this actually causes one problem later. I will mention quickly. So the story of decoupling here in a classical impasse algorithm is trying to solve this 2 primary unknown, which is the non-wetting phase pressure and the wetting phase saturation, by using the pressure equation here and the saturation equation for the wetting phase. So these 2 equations, and further, so this step is what we call decoupling step. We decouple these 2, and then we use a certain time partitioning. You can use either uniform or non-uniform partitioning, and then you can solve the pressure equation implicitly for Pn, but for all other variables, you can, particularly for SW, you use a previous value, previously time step value. So it's linear. Okay, so the right hand side is also linear for Pn, so it's a linear equation. For the saturation, we typically use an explicit algorithm for SW. The Pn n+1 here is already obtained by the previous equation. So that's why we call it impasse. Of course, there's a certain modification there. Sometimes people, for example, you could treat the second order derivative time implicit as well. That could also be possible. So in summary, in this conventional impasse, we transform the original set of equation into just 2 independent equations. One is called pressure, one is called saturation equation, to solve for our 2 primary unknowns. Now here I list a number of disadvantages, which is you probably don't see much, but many people knows in this field. Even when I was a student, and that's back I'm like more than 20 years ago. I was a PhD student in UT Austin. I actually discussed with my academic sister, now currently is Professor Beatrice Rivera. We are debugging one code together. Then I realized that the impasse algorithm is a conservative locally for the wetting phase, but in the code, it doesn't conserve the other phase. So I was actually puzzled. I was expecting maybe should be conserved both. Then I asked Beatrice, and she quickly replied, well, it is well known it's not conserved for the other phase. Then I asked her, why not to design another algorithm or new algorithm to such that both phases can be conservative locally. And her answer is, well, since this algorithm has been used so long, apparently it's challenging to conserve both phases. So nobody actually put the effort. So I remember that. So I'll keep this in my mind. So that's I just want, and what I just mentioned is this disadvantage is the impasse algorithm is not conservative for the non-wetting phase. Or if you choose a non-wetting phase as your primary variable, then it's not conservative for the wetting phase. So it's not even locally or globally. So it's not conservative at all. And because of this, we also have a stability issue. So the impasse algorithm typically require much smaller time step, for example, as compared to other like a fully implicit method or other improved impasse like an iterative impasse. And also the skin might produce a wetting phase saturation that's larger than 1, which is what we call out of bounds error. And typically we have a logarithm for the capillary pressure, or we apply logarithm to the saturation for many capillary pressure function model. And in this case, then you cannot, right? If you have, saturation larger than 1, then the other saturation will be negative. So then you cannot apply logarithm for a negative number. The other disadvantage is it does not correctly produce a saturation with discontinuity, which occur when you have multiple geological layer in your entire computational domain, and each geological layer have a different capillary pressure, and then we can show the solution, exact solution is discontinuous. But like you see in this equation, the saturation equation, you have second order derivative in space. It's like a heat equation. So this decoupling algorithm always define a continuous saturation in space. So you cannot get the correct solution. For this, actually, Hotet Ferzabadi actually published a paper and the published a modification by impasse to correct this. So this is also semi-implicit, but they basically remove the second order derivative in space term to the pressure equation from the saturation equation, therefore allow for discontinuity for the saturation in space. But this HF algorithm, again, also inherits all other disadvantages of the conventional impasse. So this, I think, what we want to achieve in our semi-implicit algorithm, or semi-implicit. So our algorithm, we want to have a locally mass conservative for both phases, and also have a bound preserving property for both phases as well. And we also, in addition, we want it to be an unbiased treatment. So you don't have to select which phase is your reference phase, right? So you can either use wetting or non-wetting as your primary variable unknown, but the numeric solution should be identical. So that's what we call unbiased treatment. So the key idea in our algorithm, which I think I'm gonna spend like 10 or 20 minutes to go through, is to derive the pressure equation, not from the PD level, right? So conventional impasse algorithm, we first derive the pressure equation by summing the saturation, the two conservation law at the PD level, and then we discretize the pressure equation. Then you can see you could have some inconsistency in your discretized pressure equation and your discretized saturation equation. In our approach, what we do instead, we discretize both such conservation law first. So we have a saturation, we have wetting phase conservation law, non-wetting phase conservation law. We discretize both of them in space, okay? And then we sum them in the discretized level to form the discretized pressure equation. In this way, we don't need a pressure algorithm. The pressure equation algorithm automatically is generated by our conservation law algorithm, or the transport algorithm. Okay, yeah, we have a series of paper that to study a different version of this new algorithm. So this new algorithm framework. So let me first talk about, so actually the three of them, the FC impasse 1, 2, and the P impasse. So let me just focus on the first one. So assuming you're using, for example, this RT mixed finite element method for your spatial discretization. So this is your space we're talking about. Now, now we define W alpha as minus k times this gradient term plus gravity. So if you multiply this W alpha with the mobility lambda alpha, you get the Darcy velocity for the alpha phase, of course, right? Yeah, so but in our algorithm here, we treat W alpha as the unknown of interest. So the following algorithm depends on the assumption that W alpha in HD space, P alpha in L2, S alpha in L2, and so on. So we define this bilinear form, which is trying to describe the convection term in your saturation equation by using upwind. Or since it's lowest order RT, so then you could only have a boundary term. So then we use a star to denote the upwind value. So we because we treat both conservation law using this binary term. So we're allowed to use upwind for both phases. This is what is not done in a conventional impasse. Conventional impasse can only upwind one phase. So now the algorithm is like this. So by using this binary form we just defined, we can write the conservation law discretizing space as the equation, the first equation here. And the second equation is the discretized Darcy's law, which you typically see by using a mixed finite element formulation, right? For that, of course, but for each phase. So you have 4 equations. Then you have the summation constraint and also the saturation. The pressure difference between 2 phases is the capillary pressure, and we can project to our finite element space as well, if needed. And then of course you need an initial condition. So this FC impasse of the first type now is formulated by just solving all the equations together. I put in this slides where we treat W implicitly, of course W alpha, P alpha, both implicitly. The only explicit treatment is S alpha. Okay, so this of course is in a similar manner as in the conventional impasse. So looks like it's a totally coupled system, right? All coupled. But fortunately, if you look closer, you can show quickly it is equivalent to a decoupled system, which I can show follows. So basically, you can sum the two conservation law. Then you get the equation 1.5. Then you can also sum the Darcy's law. Then you can couple with this to solve for the pressure and the W. And also WC can also be defined by using the define WC as the Wn minus WW. You can relate WC with PC, and PC is function of SW. So then the algorithm can be discretized. Can be shown as following 3 steps. So the first step, you can using the previous saturation value in your previous time step to get your PC and WC. By getting WC and PC, then you're solving 1.9 and 1.10, these 2 equations simultaneously to get your pressure for wetting phase and the W for wetting phase. Notice W is not a Darcy velocity yet, so it's differed by the lambda W. And it's kind of the driving gradient, driving force. And then you can update your PN and WN. And then the step 3, you can use approach 1 will be update SW as usually as in our conservation discrete conservation law. And then you get the SN by just 1 minus SW. And you can also of course update by using 1.12 and 1.13, which is using the conservation law for each one. And of course, since our pressure equation is formed by summing 1.12 and 1.13, so we can easily see approach 1 is equivalent to approach 2. So in other words, you can just use 1 minus SW to get your SN, and still your SN satisfies the conservation law locally. So that's why we achieve local mass conservation property locally in each time step. So of course, then we first want to show that these 2 approaches, step 3, are equivalent, which is easy to say. I already mentioned that, and this actually indicates our algorithm is unbiased and also locally conservative for both phases. So that's a first type of this FC impasse. The second type, the only difference, the second type is we, instead of using W alpha as our primary unknown, now we define another one, psi alpha. Psi alpha is equal to lambda T times W alpha. We assume psi alpha in HDF space instead, but W alpha may not be in HDF. And then we can go through that definition of the algorithm again. And the advantage of this algorithm, of course, is more physical. We feel, because, for example, if you do not have gravity nor capillary pressure, and then the psi alpha will be the same as our total Darcy velocity, so which is indeed sitting in HDF space, right? But the previous one, W alpha, is still not in HDF space physically. So this second type is more close to physics. We can also show this for both types. We have this local mass conservation property, as well as we interested in enough. We also can prove the boundary preserving property, conditional, of course, because it's semi-implicit. Conditional means the time step, we have a certain time step constraint. Yeah, we noticed that if you have a strong capillarity or gravity, and particularly if a countercurrent flow, then psi alpha may not be HDF. So the previous 2 methods may not be that good. So this motivates us to study another algorithm, which we think is more even close to physics further. This is what we call physics preserving impasse. So in this algorithm, the primary unknown we use is not U alpha, not W alpha, not even psi alpha. So we use psi C and UT. UT certainly is in HDF space. we know the exact solution in HDF, but XIC is not, but we still assume because we need to derive certain algorithm, just like a conventional impasse, right? Conventional also assumes certain variable, which is not in H impasse or HDF, but they assume it in HDF so that you can design the decoupling algorithm, right? But we believe that the crime we commit is much smaller than the other algorithm. So, so you could also define some bilinear theorem, you upwind both phases, and eventually get an algorithm like this. Due to time, I'll quickly jump to the algorithm part. So this is what we call P-impasse algorithm. This algorithm will also have 3 steps. So first step, we calculate the XIC and the PC. And then in step 2, we solving PW and the UT. So pretty much mimic the conventional impasse, but however we treat the both phases unbiasedly. In the third step, we just update SN, SW, and SM. And of course, we show our method is conservative for both phases, which the property does not have, conventional impasse. And also, we also have the boundary preserving property conditionally. So due to our time, I just want to show quickly one example, just comparing our algorithm with conventional and also with HF, the rotated Further body impasse algorithm. So we use the same time step. So our scheme is pretty stable, right? But if you use this HF impasse, you get overshoot. So the situation is negative and bigger than 1, or this out of bound. Of course, for conventional impasse and HA impasse, if you reduce the time step sufficiently small, you can still get a stable numerical algorithm. But the point here is we compare the time step. If you the same time step, our method is gonna much more stable. So that's the first part. We still have some time, so I want to also talk about another area we're working on for the same problem, solving the multi-phase flows in porous media, sometimes even multi-component multi-phase flow. So this different approach is fully implicit. Fully implicit method is also believed to be some scholars believe this is the future of reservoir simulation, right? They thought about if you have a very good nonlinear solver, right? You should do fully implicit, and fully implicit algorithm gonna win eventually, but even though may not be right now. So that's why we also put a lot of effort in this area. So fully implicit algorithm, so you can solve, for example, the saturation equation implicitly, and therefore even if you come up with pressure equation, it's okay, right? So you can easily enforce the local mass conservation for both phases easily if you for two-phase flow. So for phase-wise conservation, it's easy for fully implicit algorithm. However, for bound preserving, it's not easy. Bound preserving, even for I think most of the study, for bound preserving algorithm, they focus on fully explicit algorithm, not even for semi-implicit nor fully implicit. And also because of fully implicit algorithm, you solve all the variables together. And if you have a lot of components, say, for example, you have solving composition of multi-phase flow involve 100 hydrocarbon components, then a lot of unknowns. So this require parallel computing, right? So that's why our focus is a parallelized algorithm for fully implicit bound preserving reservoir simulation numerical algorithm. So we started this effort in 2016. So I think 2015. The first paper we get out in 2016. Then each year we have 1 or 2, sometimes some years 3 papers published for this framework. So, but we tackle different either different model or different design different nonlinear preconditioners. So the framework is like we want the algorithm to be locally mass conservative for each phase. If you're doing multi-component composition of flow, then we will require the locally mass conservative for each component. Of course, this some people argue this is easy to achieve, but we also want to require is bound preserving. For saturation, the bound should be between 0 and 1. For concentration, it should be larger than 0, right? And for certain equation of state, you also have maximum bound for your concentration and molar concentration as well, right? Because of the repulsion term. And for mole fraction, the bound is also natural between 0 and 1. This must be strictly enforced, because otherwise you often have take a logarithm for this value. Like for saturation, you take a logarithm, you get your capillary pressure, or sometimes also the relative permeability, right? And if you get a negative saturation, then you don't know how to do take a logarithm. And for multi-component compositional multi-phase flow, and then most of the equation state to calculate the energy. Like for example, if you want to calculate the Helmholtz energy or fugacity, you also have a logarithm for the mole fractions. And then if you predict minus 0.3 for your mole fraction, then you don't know how to proceed further. So that's a really a very important or sometimes people call it a very headache for really engineering problem if the algorithm is not bound preserving. Of course, in practice, I mean, for the impact for the fully implicit algorithm using the industrial software, they do not have the bound preserving property. Then what do? They just apply a cutoff operator. Whenever they see, for example, saturation less than 0, they cut off, they move back to 0. Of course, by doing this, they are violating the mass conservation law. You can view this like artificially add some material, so they do not have a global conservation even. So that's not what we want, even though it's widely happening in practice. So of course, so what we did here is the algorithm is bound preserving. So we use a fully implicit framework. So the bound preserving part, we actually implement that in certain inequality. I will show you. Yeah, I think that because of the time, I can there's some motivation and the challenge. I think probably I can quickly jump through. I want to just mention, if you want to do a fully implicit algorithm, the nonlinearity causes a nightmare. And in our problem, there's a lot of nonlinearity, and the nonlinearity is strong and also unbalanced. That's caused a problem. And the out of bound issue, particularly for saturation of mole fraction, also an issue. So our proposed algorithm is I think yeah, I just go directly to the algorithm part. So of course, our algorithm will apply to different kind of model, but because of time, let's assume we only look at this compressible two-phase flow, but still fully immiscible. So if you do a spatial discretization together with a fully implicit time stepping without any decoupling, of course, you get a nonlinear equation system to be solved, right? For most of approximate finite difference, as well as most of finite element method, the equation actually corresponding to a certain minimization problem, right? Without the inequality. So what we did here different is we just add the inequality to the minimization problem, and now with some derivation, we show this equivalent to force this original equation together with some Lagrange multiplier, and then you have an inequality for the Lagrange multiplier, right? So this first order optimal condition, and of course, if you remove this Lagrange multiplier, you return back to the original system. So in other words, we somehow modify the numerical algorithm. So some people argue that, well, is this equation actually you solve the original equation or not? So the answer is well, sometimes may not. Sometimes we even modify the original PDE. So because sometimes if the PDE is not bound preserving, right? Sometimes we cannot prove. But if the PDE is bound preserving, we do not modify the PDE itself. We only modify the algorithm. Our algorithm is not only we trying to get the bound preserving variable, within each time step, but I also want to do this for each Newton iteration step, because otherwise you still have the same trouble, right? You take a logarithm for this negative numbers, which you don't want. So what we do here, consider the conventional Newton's method, where you find Newton method is to solve nonlinear equation. But if you view from the optimization viewpoint, it's like you minimize a certain energy on a certain space, right? But in certain dimension, maybe corresponding to the situation where can go to negative. So our method, if we identify such dimension, we remove this dimension from our searching space. So our space is reduced. So that's why we call our method reduced space method. And we maintain an index for all those dimension, which one is active, which one is inactive, right? So that's why we call this method as the active set reduced space method. And the nonlinear solver look like this. So I just mentioned about the active set reduced space method to maintain the bound preserving property. We also actually apply another nonlinear preconditioner to our system to speed up the convergence of nonlinear iteration, because that we have a unbalanced nonlinearity. Certain variable can converge quickly by Newton iteration, but other variable very slow. And then if you solve them together in a single iterative algorithm, then it's kind of like a multi-scales, multi-rate convergence. So it's slow. So instead of doing this, we remove the bad variable first, and by nonlinear elimination, of course, numerically as a preconditional. And because of time, I will not to go into detail on the nonlinear elimination part. And for the so when you apply this modified Newton's method, you basically convert the nonlinear equation system to a large linear sparse equation system. We use domain decomposition as our preconditioner, such that this algorithm can be easily parallelized. And we also actually study some different variation and use our numerical test to compare. So yeah, because time, I think I just quickly show you the one of the 2D results showing using SP10 permeability and porosity, and testing different injections from the side, from the well, and then compare our method from existing method, and also compare our own method but with different conditions. Of course, if you have and this capillary pressure and nonlinear, this is strong nonlinearity gonna increase your nonlinear and linear iteration, typically nonlinear iteration particularly. And the second example is just trying to show you even in 3D, we our method scale well, and we actually compare the total computing time with a number as a function of the number of process cores, as well as the speed up as a number of process core. So it scale quite well. Okay, so in conclusion, that today I present a fully conservative numerical algorithm and also bound preserving for multi-phase flow, but I focus on a simple one, this two-phase flow. But of course, the idea easily extended to other multi-phase, multi-component of flow and transport, which we have papers. We don't have time to present here. So if you're interested, you can look at the papers. So because of time, I focus on most of my discussion in a semi-implicit algorithm, where we derive this decoupling by the major thing is we derive the pressure equation discretely at a discrete level by summing the two conservation laws at a discrete level, and then depends on which intermediate variable you choose as your primary unknown, which you assume to be a HDF space, then you end up with different numerical algorithm, a different variation of the algorithm. Fully implicit method I want to comment on is also a very interesting research direction, of course, and I think because you can easily impose the local mass conservation for all phases and all components. For boundary preserving, then I think if you want to just change the numerical scheme, it's very challenging to achieve. So what we did here is we utilize the energy optimization principle and to enforce this as an inequality condition. And in this way, our scheme, fully implicit scheme, is not only so I want to emphasize our bound preserving property for the fully implicit algorithm is unconditional. So no matter how large your time step, is always bound preserving. Some future work I want to mention, of course, extend this to more complex model, particularly the model involving fracture, which we haven't got the time to do it yet, and also to high order approximation in space. And also we also think that we can combine the impasse, the semi-implicit method to the fully implicit, to use the semi-implicit as one of the precondition for the fully implicit. And I also want to thank the funding agency for the research, particularly KAUST, the KAUST, which is a Saudi version of NSF, and Saudi Arabian company, Dow Chemical Company, and many others. So I think that the time's up. I'd like to thank you for your patience, and if you have any comments of interest or questions, I'll be happy to hear and answer. Thank you.
Thank you, Professor Sun. Thank you for your great talk. So any questions from the audience? You can simply unmute yourself, or you can type in the chat box. Maybe I can start with a simple question.
Okay, please go ahead.
Yeah, so when you do the decoupling, what about the accuracy of the method in terms of the time?
Oh yeah, that's a very good question. I forgot to mention about this. Well, the time discretization error for our semi-implicit algorithm is the same as the conventional impasse. So it does not, so it's the same order. I mean, I'm not sure if we can improve or not, but from the proof you can easily see it's a same order. But the point is that for multi-phase flow in porous media problems, we choose we choose a time step majorly because of stability control, because of stability reason. Otherwise we want to use a larger time step. So the time discretization error is already small enough as compared to the stability issues. So stability is the reason why we have to choose a small time step, not the time discretization error. That's why all the design here is focused on improve the stability of the algorithm. So you're right. Yeah, as a computational mathematician, we still have to talk about the error from the time discretization.
Yes, thank you. So the second question is, could we apply this idea to some high order time stepping scheme?
Yeah, that's a very good question. I think which one you actually ask, the fully implicit or the
semi-implicit? I guess so. Yeah.
Yeah, the semi-implicit algorithm. Yeah, I guess so. I guess at least certain this linear version of the multi-step linear version. So you only solve linear equation each step, but you have a multi-step like a Runge-Carter kind of time stepping. I think for this kind of framework, I think our method should work out. But for other, I have to rethink. Yeah, we haven't put any efforts on high order time stepping yet, but that is really important and interesting area to work on.
Yes, thank you. So any questions from the audience? please feel free to ask any questions. Yeah, we have one question in the chat board.
Oh yes, I'll also see that. So the question is about the compressible flow. Does this scheme to applicable to a compressible flow? Oh yeah, the answer is yes. For the semi-implicit algorithm, just for convenience, we use incompressible flow. We also have a paper talking about compressible flow as well. Yeah, this is applicable. And for the fully implicit algorithm, the model we show is already compressible flow. Yeah, the answer is yes.
Hi, Professor. I just have one more question. So can you hear me?
Yes, I can hear you well. Go ahead.
Thank you. I just curious about so this scheme has already been applied to compressible flow. So does any specific procedures in this case that need to add it from the incompressible flow?
Are you trying to asking the algorithm of the fully implicit one or the semi-implicit?
About the semi-implicit.
Yeah. For the semi-implicit algorithm, yeah, if you have a compressibility in the fluid, it actually causes a little bit more complexity in the algorithm, because you know, when you add up the two equations, the time derivative does not disappear. So you do not end up with the elliptic equation, right? You still end up with some kind of a parabolic equation.
Yeah.
So yeah, so we, but that term can be related to the pressure, right? So you use fully so for example, if you use implicit Euler method for treating that term, and you then you still end up with equation implicit treatment for the pressure, so you can solve for the pressure globally.
Oh, okay. Thank you, Professor.
Yeah, thank you for the questions.
If no further questions, let's thank Professor Sun again. Thank you so much for your great talk.
Yeah, thank everyone for your time and patience. 好，那我就下线了啊。
好的，孙老师，谢谢您。
Thank you.
谢谢各位老师。
Yes.
Yes, thank you.
好，谢谢毛老师。